Well, I'd paused in the middle of page 40 on some of the examples because I wanted us to have a bit more time to discuss some of the other applications that we can use with cross product. So this example here asks us to find the area of the triangle determined between 3 points. Now let's just draw these points. I'm drawing them arbitrarily. I'm not drawing them where they actually would go on our three-dimensional coordinate system. And so when I've got these 3 points, I could actually determine vectors between these points. And from there, once I have 2 vectors, I could get a parallelogram or a triangle between them. And we can recall that the area of a triangle is half the area of the parallelogram. Well, as it was stated previously, the area of the parallelogram is the magnitude of the cross product, so that means that this is going to be 1/2 the magnitude of the cross product, and that's through these vectors that I need to determine. So using our points, now recall when I want to find vector AB, I have to go B minus A. So we would say from the origin of B, origin to A, and we'd subtract. And that would give me what? -1 minus 2, so -3, -2, +2. And then if I want vector AC, I've got to subtract origin of A to origin to C minus origin to A. And so from C, that gives me what? -2 for my +2 and 3. Okay, well with these two, I now need the cross product. So I'm going to line them up and determine my cross product here. So cross out the first column. -2 times 3 is -6 minus 4. Then I'll have -4 minus -9, so +9. And last I'll have -6 plus, nope, -6 minus 4. So -6 minus 4 gives me -10, +5. And another -10. And that is my cross product. So then taking this up here, I'll find that the area will equal 1/2 times the magnitude of that vector, which will be 1/2 times the square root of -10 squared plus 5 squared plus -10 squared, which I believe is square root of 225, which is 15. So the area is 15 over 2 square units. Now we can actually keep going with the cross product, and we can go one up from area, and we can look at volume. And so what we have here is, if I had my vectors u and v, then we know that the cross product down here would be the area. So here's my area, would be U, magnitude of U cross V. Okay, well, when I then take another vector W and I put the initial points of U, V, and W all together, I can actually form this parallelepiped. That is actually the real word for it, parallelepiped. In a way, it's a box or a rectangle that is formed by parallelograms. So what we have here, though, is that our volume of this parallelepiped is going to depend on our height. And our height is going to depend on then the angle between W and the vector U cross V. So we're being told that our volume formula is equal to the absolute value of W dot U cross V. So let's see if we can prove that. Well, we can start by saying that the area of the bottom, in this case of the parallelepiped, is the magnitude of U cross V. H, being our height, can actually be determined by the magnitude of W times cos theta if we make sure that it's an acute angle, so it's less than pi by 2. So from here we could say volume will equal, well, I'll take the area of the bottom and multiply it by my height, which is the magnitude of W times cos theta. Well, since, oh, you know what? I'm just going to, I notice right now that I actually used the angle phi right there. So I'm going to come in here and just change those to phi so it matches the picture, okay? Not like it really matters. It's like a variable. It's like a placeholder holder. So since phi is the angle between W and the cross product U cross V, then I could actually state here that this is equivalent to saying U cross V dot W. So recalling our formula for finding the dot product that we had, like the magnitude of one angle times the magnitude of the other angle times cosine, well, that's equivalent to saying the dot product between those two angles. And we could also just rearrange this because dot product is commutative. All right. Now, we can say, though, that if my angle is, in fact, obtuse, then you can show that the height would equal the negative. So we would have like an obtuse angle, so it's larger and it would come around the other way. And so then, in fact, our cross product would be going in a different direction, so we'd have this negative. And the result follows. So if it's going in the other direction with negative, then it would follow then that the volume would need to just be the absolute value. So we state the formula using the absolute values as kind of just a catch-all to make sure that we're not going to forget that we want to state volume as positive in all situations. Now, just one little remark at the bottom, though, is that if any of the vectors u, v, or w is 0, then the volume's also 0, because we don't get volume from a zero vector from nothing. Well, let's look at an example here. It's asking us to compute the volume of the parallelepiped. Okay, well, I'm going to start by finding U cross V. So I'm going to line them up, -1, 0, 1, 1, 2, 2. I'll get 0, because 0 times 2, minus 2 for the first component, of 1 plus 2 for the second component, and I'll have -2 plus 0 for the third. So -2, 3, and -2. Okay, well, let's go W dot U cross V. So that's going to be 0, 1, -5 dot -2, 3, -2, which will give me 0 plus 3 plus 10, which equals 13. And then I have to remember to make sure my volume is positive, and it is. So the volume is 13 cubic units. Now, just a note that in a testing setting, it would be very easy for me to see if my students have memorized a formula versus actually understand really that volume has to be positive. If I made sure that my volume would turn out negative, just to make sure that they would use absolute values. Those are the type of things that math professors like to put on tests. Well, just to conclude here, though, is this idea of coplanar. So we've talked about collinear, meaning that it's parallel. Now, coplanar means that the volume of the parallelepiped between them is 0. So that means like the vectors u, v, and w aren't 0, but that the volume between them is 0. So for example, in our previous example up here, we found that the volume equaled 13. So they're not coplanar. And by coplanar, I mean falling on the same plane or lying on the same piece of paper. If they're lying on the same piece of paper, then I'm not going to be getting volume to there. All right? Let's determine if these vectors are coplanar. Well, I would start by going U cross V. So I would line it up. 1, 2, -5, 1, -2, 2. I have 4 minus 10. I have -5 minus 2. And I have -2 minus 2. So I have -6, -7, and -4 as my vector. And now I'm going to go U cross V dot W, which will be -6, -7, -4, dot 2, 0, -3, which will give me -12 plus 0 plus 12, which equals 0. And we would say that thus U, V, and W are coplanar. Or in other words, these three vectors don't form anything that has volume, and so they must all lie within the same plane.